Hello everyone, welcome to Scholar Lab. Our simulations can transform your teaching approach, making lessons much more interactive and captivating for your students. Scholar Lab is a distinctive virtual laboratory that brings intricate STEM concepts to life through engaging simulations. This tool is crafted to aid students in comprehending and applying scientific principles in practical situations. In today's simulation, we'll explore how a DC motor works and what factors can influence the rotation of its coil. This interactive experience will help you to dive into the fascinating world of electromagnetism and mechanical movement, where the electricity and magnetic fields come together to set things in motion. Let me open DC motor simulation for you. Each simulation begins with a game plan. This outlines the procedures, observations, and learning of the simulation. If you are a new user, kindly go through this section thoroughly to maximize your experience. Our main objective of this simulation is to explore how a DC motor works and the factors that can affect the rotation of its coil. We'll begin by visualizing the inner workings of the DC motor. We have a red line between the north and south poles of the magnet showing the magnetic field. Let me place the battery in the correct position by dragging it. The green arrows represent the current flow. The interaction between these two, the magnetic field and the current, creates a force that turns the coil. Let's take a moment to understand Fleming's left-hand rule. You may have heard of it. It helps us to figure out the direction of the force on the coil. If your index finger points the direction of the magnetic field, and the middle finger points the direction of the current flow, and your thumb will point the direction of the force on the wire. Now, based on this, you can predict which way the coil will rotate when the current flows. Let's move to the interesting parts of the simulation. Want to make the things even more interesting? You can change the terminal of the battery by clicking on this symbol. I'm placing the battery again after rotating the battery. When I flip the battery terminal, you will notice the direction of the current flow reverses. This in turn causes the direction of the force on the coil to reverse and the coil spins in the opposite direction. Now check out the dial in the bottom left corner of your screen, labeled angular velocity. This measures the strength of the turning effect on the coil, which is directly proportional to the force acting on the coil. As the force increases, the coil spins faster and the angular velocity rises. It's time to experiment with other variables. What do you expect will happen if we increase the power of the battery? We can do this in this simulation. By clicking on this arrow mark, it will drag the variables of this experiment at the battery's magnetic size and the coil size. Now let's turn up the voltage and see what happens. I'm changing it from 1.5 to 3.7. With the more power flowing through the coil, the magnetic field interacts even more strongly now. And the coil should rotate faster. As the angular velocity increases, you will notice a more intense turning effect on the coil. Now, let's boost the power of the magnet. I'm going to place a big magnet instead of small. This will lead to a greater force on the coil, and you guessed it right, It promotes the faster rotation. You can really see the dial of the angular velocity jump when the magnetic strength increases. Next, let's explore the effect of changing the size of the coil. A larger coil will experience the bigger turning force, but it also means more resistance and a different distribution of the magnetic field. I recommend you to play around with the settings and see how the size of the coil impact the magnetic rotation. Now, next, let's experiment with the magnet. You can swap the regular magnet with the horseshoe magnet by clicking on this. When I place the horseshoe magnet, it produces a much stronger magnetic field. It increases the strength and more forceful interaction with the current. You can also see the difference in angular velocity dial. Now, what happens if we flip the magnet in other direction? By clicking on this symbol, you can flip the magnet direction. When we flip the magnet or the horseshoe magnet, the magnet field reverses. According to the Fleming left-hand rule, this changes the direction of the force on the coil. By flipping the magnet, we are changing the fundamental interaction between the magnetic field and the current, which directly affects the motor behaves. This is why when you reverse the magnet, the coil starts rotating in the reverse direction. With these factors in mind, battery power, magnet strength and coil size, explore how the motor behaves under different conditions. Try combining higher battery power with the strong magnet. What happens when you reduce the size of the coil but crank up with the voltage? As you experiment these, keep an eye on the angular velocity dial. It's a guide to understanding how these changes affect the speed and efficiency of the motor rotation. The faster the coil turns, the higher the dial climbs. Through this simulation, you are not just watching the motor in action. You are actively controlling and predicting how it behaves based on the interplay between electricity, magnetism, and the mechanical force. Each element, from the power of the battery to the size of the coil, plays a crucial role in how the motor functions. So, go ahead, experiment with different settings and discover the fascinating world of DC motor. Happy learning! Thanks for watching.